We've completed the construction of the noise generator bridge. Now we're ready to test and calibrate it. We have in the manual a summary sheet of the steps required for the testing and calibration of the bridge. You can use that for reference. First thing to do is to just make sure your batteries are okay that you put in the holder. Positive should come out of that terminal and negative out of the cloverleaf, and we're reading 9.14 volts, so that'll be fine. The next thing to do is to see if we've got any short circuits on the rail. So we'll put the ohm meter across the two terminals, and we read about 4 meg, so that's definitely not a short. That high resistance will be due to the electrolytic and maybe some of the other components on the noise board. Let's check for continuity between the battery snap and the rest of the circuit. We know the positive will come in on this cloverleaf button to match this button on the snap, and we require the switch turned on so we can probe this point where the diode is on the switch. It gets to there. Now the other side of the diode reads about 170 ohms, and similarly back here on the rest of the wiring. So we need to check from the cathode end of the diode to there, and we know that's connected, and we know it's connected to the noise generator board as well. Let's just check the earth. The earth will come in on that particular connection, and it should go to earth just about everywhere, which it does. So we know the wiring is continuous, we know we don't have any short circuits, we know the switch is working. We can now connect the battery snap and just have a quick look to see if the LEDs are working, which they are, and we can switch the receiver on and we can hear noise. So we know the noise generator is working, and if we like we can adjust the tone level here, make sure that's still going. We would have set that before. Tone off, just noise, and the bias on the diode, that can be adjusted one way or the other, but pretty well the center is alright. Bring the tone up again and adjust that bias resistor. So we know the thing's putting out noise, the LEDs work. The next thing is to align the little wheels, little dials here. They may be out a little bit, depends where they ended up. We'll use a Phillips number 1 screwdriver in the little wood screws here that go through here, and by loosening these screws we can rotate the drum, and the idea is to set it up so that the 0 on the logging scale is at one end of the pot travel and the 100 is at the other end of the pot travel, and similarly the 0 on the logging scale for the capacitor at that end and 100 at that end. For that we'll need to pop the battery in there, fit the cursor to the lid, and just have a look and see where things are at this point in time. What I'll do, I'll push the LED out of the way because they interfere with the camera exposure and we don't get a very good picture of the scales. So here we are, just zooming in. This is the capacitor dial, that in line, and that's on 100, so that's okay, and that's close enough to 0. There's a bit of parallax error here with the camera. That's it there, 0. The 100 PF marking is slightly over 0. Doesn't quite make it 100 PF, this capacitor. So we're quite happy with it, that's okay. And the resistance scale is a little bit off in that direction and a little bit over on that direction. So we just need to adjust that, which I will do. Okay, now that we've adjusted the two dials, we're ready to do the electrical calibration. First thing to do is set the two little trimmers to minimum capacitance down here. I'll just come in a little bit tighter. There we go. That's this one here, and that one there, just adjust them so that the plates are fully unmeshed. Solder a short circuit across the Z unknown connector, and first thing we're going to do is set 0 reactance at 1 meg and then 28 megahertz. So we switch the receiver on, which is at 1 megahertz, and we'll check the reactance point. Happens to come out there. We'll see where that is on the scale quickly. There we go. It's not on 0, so we set the scale to 0, turn the receiver down a little bit, and adjust the trim pot for a null. That's it there. So we've now set the 0 reactance point at 1 meg using that trimmer. So we'll just double check that. Come down a little bit on the scale. Of course the resistance will be 0 because it's a short circuit. There we go. Now we'll tune the receiver to 28 megahertz and we'll see what we've got. That's 28 meg. Wind it up. That's pretty good actually. We have a compensation coil here, which is there, and that coil you can adjust that coil so that the 0 reactance occurs on the 0 mark to 28 megahertz. If you stretch this out, you'll see that changes. Just pull a bit more out. Back to the reactance dial. You see it's back here now. So put it back under 0 here, and we'll squeeze the coil in a bit more. Just turn the gain up so you can hear it. Okay, down, go up, and somewhere in there. Seems to be about right. That's 4 turns. And just check that. So we've now compensated the bridge for stray inductance. The next step is to compensate the bridge for stray capacitance, and these two trimmers are used for that adjustment. To do that, we need to put a high value of resistance across the Z unknown. So what we'll do, we'll remove the short circuit and put a 430 ohm resistor across that little connection there. I've connected a 470 ohm resistor across the bridge. I'll just check its value with an ohm meter, see what it actually reads. It should be pretty close. So we'll just confirm what it actually says. And it's approximately 426 ohms. So that resistor reads 426 ohms. The two compensation trimmers are used to set the resistance dial at the right value with a resistance at 1 megahertz, and later on also 28 megahertz. So we'll just switch the receiver on and we'll see where the bridge nulls with that 426 ohm resistor. The reactance should be 0 because there's no capacitance or inductance, or very little associated with that resistor. So reactance is 0 and resistance reads around 385 ohms. So we have to do some adjustments. This first trimmer we try to adjust is the one near the connector up here. So we'll just see if we can zoom in on that and see what effect that has. We set the dial to 426 ohms or thereabouts. That's 420, that's 426 ohms there roughly. And we try to adjust for a null now. So this is at 1 megahertz. A slight decrease there. See if we can get a bit closer. We can rock the reactance dial to help us here. I'm rocking the reactance dial, as you can see. We're not getting much of a null there, so we'll try the other trimmer on the other side of the bridge. Here we go. So we've now set the resistance scale. Out there, and the reactance will be a little bit out at this stage. So now we tune to 28 megahertz and we do a finer adjustment, leaving the resistance scale alone. We now set the reactance scale, a bit more gain. You'll see it's way up here somewhere. So we set the reactance scale there and we adjust this trimmer ever so slightly. It doesn't take much. Barely touch it. We've now set the reactance null there. You may need to do that several times, and you can also find this one up here has some slight effect as well. Go. And a bit better on this one. I'll just nudge it that way slightly. Let's just see where we're at now. Okay. Resistance still alright. So after some adjustments on the trimmers, this is what we've ended up with the 430 ohm resistor. Frequency is currently at 1 meg. So that's roughly 426 ohms, and the reactance is 0. We'll now switch to 28 megahertz. we go. It's 28 megs. Just show that on the receiver, and back down to the dials. There we go. Bit more gain on the receiver so I can hear it. That's pretty right. And the resistance in a bit. And that's the result. Now, in order to achieve that at both frequencies, you need to do this adjustment several times. I'll just turn the receiver off. Here we go. We go down to the RF deck and we have a look at the components. What you have to do is, after the first adjustment, you'll find that the reactance control will not null at 0. It will null some slight amount off at 1 megahertz. So you have to go back and readjust this trimmer slightly to pull the set 0 back into line. You do that with a short circuit. So you'll notice the little bit of wire there. I just swing that around onto the pad, solder it, and then remove and then set the 0 again for a short circuit for 0 reactance. Of course, the R dial has to go to 0 ohms as well. And I then switched to 28 megahertz and adjusted the compensation coil a little bit more. You'll notice it's pulled out slightly for set 0 reactance again. Remove the short circuit, go back and readjust the dials, do some very fine adjustments on this trimmer here, or that one, whichever one, until you get the 426 ohms again and the reactance comes into line. I had to do this 2 or 3 times to finally achieve what you saw on the scales then. So unfortunately the trimmers interact with each other. Adjusting this one adds capacitance into the circuit, which then has to be adjusted with this, which affects the position of this trimmer, and also for the inductance. But if you spend enough time on it, you'll find that you will achieve what I've just shown you. The other thing is very important that this resistor here is actually soldered inside the bridge. If you connect the resistor on the outside of the bridge using one of the barrels, you'll find that you won't be able to achieve that sort of a null. Just to illustrate that point, I've removed the 430 ohm resistor internally just by moving it sideways, and I've connected a 470 ohm resistor inside a barrel on the Z unknown. There we go. Now I will show you the reactance and resistance readings with that barrel mounted resistor. Put the scales back on and we will set the receiver at 1 meg and switch it on. That's 1 megahertz. And we'll just zoom in. Out there on the resistance, and there on the reactance. The parallax error, it's actually 0, but the parallax error causes a problem there. Okay, so now we switch the receiver to 28 megahertz. It's the same type of resistor you saw connected across the board internally. And wind the gain up a little bit, and you'll see there's some, shows 300 pf, whatever reactance that will be at 28 megahertz. The resistance is pretty much the same, but the reactance is no longer 0. Now you find that if you take the same resistor, I'll just show the frequency on the receiver. There we go. You find if you take the same resistance and mount it internally, you will get the results I did with the 430 ohm resistor. So it's quite important when you calibrate the bridge that you calibrate it with the components as close as possible to that connector, and not have the stray inductance and capacitance associated with the barrel. The next thing to do is to check the bridge at 50 ohms. So I've connected a 50 ohm resistor inside a barrel across the Z unknown. Just quickly measure its resistance so we know what it is. And it says 50.3, the leads are 0.2, so it's very close to 50 ohms. The one in the kit will be 51 ohms. So we'll see where that ends up on the dials. We'll switch our receiver to 1 meg first, which is there, and we'll just zoom in on the dials. There we go. That's pretty good, and we'll do the same test at 28 megahertz. It's there. There we go. A little bit high, due to some extra resistance, RF resistance. Reactance is not too bad. In the case of the 50 ohm resistor, you'll get slightly better results if the resistor is actually soldered inside the bridge, but it's not as dramatic a change as the 470 ohm resistor. When you have a high resistance or high impedance across the Z unknown, the effects are much more pronounced. The effects due to stray capacitance and inductance are much more pronounced. At lower values of resistance like 50 ohms, it's not so bad. So having the resistor in the barrel isn't as big a problem as it is, say, a 470 ohm resistor. There's one last adjustment you may need to make, and that is to set the minimum capacitance on the reactance scale at 20 picofarads, which is there. To do that, I've included in the kit a couple of 20 pf plus or minus 2% ceramic capacitors, and I've soldered them across the Z unknown connector. I've set the receiver at 28 megahertz and set the R dial for 0 and the capacitor at fully in one direction. Now at the back of the trimmer, back of the tuning capacitor, there is a couple of trimmers that you can adjust. Now these are a little bit awkward to get into, unfortunately, because of the location. But as I adjust these trimmers, you'll hear the null come in and out. That's one way. You see that okay? I'll just zoom in a bit tighter. Okay, so this one here, you can do either of them. It's one way. That's the other way. You see the black mark, which represents the 20 pf. Okay. So we know the capacitor is nulling with 20 pf across the bridge at that location. There we go, it's a bit better. So you'll need a screwdriver like this to do that, and as I adjust the reactance dial, you can hear it pull out of the null. So we know that if we place a 20 pf capacitor across those 2 points, that will read correctly. It won't make much difference to the rest of the dial, it's just a very fine adjustment. Just one final note on the adjustment of the 20 picofarads limit. If you find you had to adjust it several pf, you may find that the zero reactance point has shifted with the short circuit termination. So just put the short circuit back on, tune your receiver to 1 MHz, adjust your trimmer to bring that into line, make sure your R dial is at 0, go to 28 MHz, and just slightly touch your coil if you find that's out as well, and try then test your 430 ohm resistor. You'll find the 430 ohm resistor will probably be alright. Unfortunately, all these capacitors interact with each other, and a slight adjustment here will cause a slight shift there and so on. But by doing this a few times, you can eventually get it quite good.